Hi, this is Ms. Delosier, and this is going to be a review of calculating chi-squared from your FlyLab genetics problems. So if you go on to the FlyLab genetics, there's a statistical analysis review, and I'm basically just going to walk you through the first question on there. So if you want to go back and try it and see if you get the same thing that I get, go ahead and stop the video, go back, look at that, and then you could work through it at the same time. So this is the question, and I just screenshotted it from the website. It says, consider corn seedlings resulting from an F1 cross between parents that are heterozygous for color. So I'm going to look at a Punnett square for the F1 cross, big G little g by big G little g, and I'm going to predict the expected proportion of green to albino seedlings that would be 3-to-1. That is my hypothesis, that it's 3-to-1. And that's kind of like the null hypothesis in this case, because we're saying that green is dominant over albino because big G is green, right, and little g is not green. And I know that the big G is green because G green, and you name first letter of the dominant trait, right? So for this exercise, we're going to go ahead and fill in the expected. Now at this point, you should have already actually done all of your predicting how it's inherited, and I'm just walking you through how to figure out what the expected number is and actually how to do the chi-squared. So let's say that I took green and I crossed it by an albino, and I did the F1 cross, and I did the heterozygote by the heterozygote, and what I get is that 3-to-1-ish ratio. And I want to know, is that really a 3-to-1 ratio? So my question is this data truly in a 3-to-1 ratio? That is my null hypothesis, that this data agrees with Mendel's predicted results of that Punnett square, the normal Punnett square that you're all thinking in your head. So if I look, I have two possible phenotypes, green and albino. I see 72 green and 12 albino. Now, that means that there's a total of 84. So how do I figure out what the expected number is here? 3/4 of the answers in that Punnett square, I'm going to have one homozygous dominant and two heterozygotes in that Punnett square, right? If you set up that Punnett square, 3 of the 4 squares are going to be big G, or big G, little g. So what that means is that that I'm going to go ahead and I'm going to expect 3/4 of my total of 84 to be green. 3/4 of 84 is equal to 63. So my expected number for green is 63. I got 72. That's pretty close, right? But is it statistically close enough? Now, I'm going to do the same thing for my albino. 1 out of the 4 squares in the Punnett square would be little g. So that means that I'm going to expect 21 because 1/4 of 84 is going to be 21. Or you could just subtract from 84, right? Because it needs to equal 84. So I'm going to have 63 expected green and 21 expected albino. And I'm actually not going to fill in that OE column on this slide. I'm going to do it on the next slide. So that is how you do the expected number. Now, we have the chi-squared formula. It's on your formula chart. So in order to do the statistical test, what we're going to do is we're going to fill in the rest of the chart. Remember, I'm expecting 63 and 21. So if I do observed, 72 minus expected, 63, I get 9. If I do observed, 12 minus expected, 21, I get -9. And it's almost always going to happen that way when you're looking at only 2 in the genetic crosses. If you've got 3 rows in your list of phenotypes, it's not going to always happen that way. So then I'm going to do observed minus expected. So squared. So 9 squared is 81, and -9 squared is also 81. Now there's a typo on the website. It says O minus E quantity squared divided by 2. It's supposed to say observed minus expected quantity squared divided by expected. That's supposed to be an E. That's important. If you do it as 2, you will get the wrong number. So we're going to do 81 divided by expected, 63 gives you 1.29, right? And then you're going to do 81 divided by the expected number of albinos, 21, is going to give you 3.86. And then what you do is you total together that column. You just add them up. So I added 1.29 to 3.86, and I got 5.15. So my chi-squared value is 5.15. The name of the test is a chi-squared test. Do not take the square root. Leave it as chi-squared. Chi-squared equals 5.15. What does that mean? Is that significant? I don't know. We have to go to the next slide. So chi-squared is 5.15. So we have to look at our critical values. So this is where the way that you have it set up on your charts in your packet makes it easy. What you're going to do is you're going to look at the number of phenotypes. Here we had green and albino. And you're going to do the number of phenotypes minus 1. And you will always do the number of phenotypes minus 1. So 2 minus 1 equals 1. So I have 1 degree of freedom. So I'm going to look at the column that says 1. And I'm going to look and see if my chi-squared value is less than or greater than that critical value. And you'll see that my chi-squared value is going to be greater than that 0.05 value, because the 5.15 would go in between the 3.84 and the 6.64. Everybody sees where it goes, right? So here's the deal. If chi-squared is less than 3.84, what that lets you know is that there's like a 95% chance that my data is normal, right? Because like 0.05 is like 5%. But what you're telling me is 5.15 is between 5% and 1%. So you're telling me that there's a less than 5% chance, right? There's a less, that's supposed to say P is less than 0.15. I'm sorry, I don't know why it says P is greater than 0.15. That's wrong. Less than. So there's a less than, the probability is 0.05 to 0.01, somewhere in there, right? So that means that there's a less than 5% chance that my data is normal. So what does that mean? Does that mean that I accept my 3-to-1 ratio as being true, or do I reject it? So if there's less than a 5% chance of my 3-to-1 ratio being true, then we reject the null hypothesis. So in this case, you're going to look. If chi-squared is less than 3.84, you accept, or what you say is you fail to reject the null hypothesis. If it is greater than 3.84, you reject the null hypothesis. And I do want to talk about that phrase, fail to reject the null hypothesis. You can't really accept the hypothesis, you fail to reject the hypothesis. And that's fancy talk, but I am going to make you guys start using that. So again, you find the 3.84. If it's above 3.84, hypothesis is fine. If it's below 3.84, bad hypothesis, okay? I will work with you individually on those, and you could also go ahead and watch the statistics video that Mr. Anderson has, and you can go through the other statistical analysis problems later on the website. Also, the FlyLab has the statistics online, so you could probably actually just play with the FlyLab thing online and figure out a little bit more about that. I hope that helps and you're not too complicated or too confused by that.